This video guide is going to take you through how to do a simple one-way within subjects ANOVA. The data included here is based upon some research that was published that came out of the University of Liverpool. So this experiment is relatively straightforward. You can see in your data set, we've got 4 columns of data. We have sub, which is simply our subject or participant number, and as you can see we had 31 participants. Because it's a within subject design, each participant contributes multiple data points to our data set. And what these variables essentially mean, they are scores in a variable fluency task. In the variable fluency task, participants simply have to say as many words as they could, beginning with certain letters, within a minute. And the scores you see here are simply the number of words our participants managed to produce. They did this under 3 conditions. They did it after consuming alcohol, after consuming a placebo drink that smelled like alcohol and tasted like alcohol but actually did not contain any alcohol, and a control drink which was simply water. As you can see, if you look at the variable view on this data set that's available to you, they are all labelled in the label view there. So what we're interested in here is whether there is a difference between the number of words produced following alcohol compared to the placebo, alcohol compared to the control condition, and the placebo compared to the control condition, i.e. do the drinks consumed have any form of effect on verbal fluency. And what you'd expect, of course, is following alcohol, people will produce less words than after the placebo drink or the control drink, because alcohol interferes with the ability to do complex tasks. So to do this analysis, it's a relatively straightforward matter. We need to go to Analyze and General Linear Model, and then we go to Repeated Measures, because this is Repeated Measures ANOVA, because we are repeatedly measuring the same dependent variable but under different conditions. Our dependent variable being words produced, and the different conditions being alcohol, placebo and control. So this now opens our Repeated Measures Define Factors window. This is basically where you're going to label what your independent variable is called. So a logical name for our independent variable will be drink type. How many levels does it have? Well, it's straightforward. We have 3 levels to this independent variable: alcohol, placebo and control. So we have 3 levels, and then we click add. SPSS now knows to expect a variable that we've now called drink type, and it's going to have 3 levels too. We then click define. This is where you should be telling SPSS what variables in your data set are related to the different drink types. So you can see it's got question mark 1, question mark 2 and question mark 3. So once drink type 1, drink type 2 and drink type 3. For a simple within subjects ANOVA, it doesn't really matter what order you put these things in. It would matter if it was a complex within subjects ANOVAs, i.e. if you had 2 or more independent variables, but in this case it really doesn't matter. So we can just click them all across together in order. SPSS now understands that you have 3 levels to the drink type, and they are represented by the alcohol variable fluency, placebo variable fluency and control variable fluency columns. There are a few other things though we should be asking for. If we go to our options, this gives us this window here. First of all, we're going to ask for descriptive statistics and estimate of effect size. We don't need to select homogeneity tests, because homogeneity of variance cannot be an issue for within subjects ANOVA. We do need to ask for some other things though. What we need to do, we wanted to display estimated marginal means for drink type, and then click compare main effects. This is actually going to give you your post-hoc tests. So confidence interval adjustment, you see the choices here. We've got the least significant difference test, that's no confidence interval adjustments, Bonferroni. So that is going to adjust your p-values according to the number of comparisons, because you've got 3 conditions. This means there's 3 possible comparisons: alcohol versus placebo, alcohol versus control, placebo versus control. So what SPSS will do will be multiply any calculated p-value by 3. This makes it, of course, harder for you to find a statistically significant result. In this example here, we're just going to stick with the least significant difference test. And then we can click continue. There are a few other things that we could ask for. We could ask for plots, in which you can simply ask for drink type on the horizontal axis. Of course, don't forget to click add. If you don't click add, it won't actually give you any plots at all. And then we can simply click OK, and this will give us our output. So the first thing it does is give us this table, your within subjects factors. This is just basically saying how you've set up your within subjects variable. It's often worth checking this just in case you've clicked across something in error. For example, you may put subject, the sub variable from the dataset, in here in error. It's really important to check it when you have more complex within subjects designs, say 2x3 or 2x3x3 design, because you need to be really careful in the order you put in your variables. As you can see here, it just says we've got drink type, it's got 3 levels, and this is what we've said those dependent variables are. Next table is your descriptive statistics table. So you could report these in a table, or you could report them in text while writing up results. If you've done them in a table, of course you wouldn't repeat the same information again within the text. So we can look at our means and standard deviations for our conditions, report them to 2 decimal places to be APA format. The next table is the multivariate test table. So you can see this contains things you're familiar with from an ANOVA. F values, degrees of freedom, significance, and partial letter squared. However, we don't really look at this table at all when it comes to within subjects ANOVAs. Some people do, some people would report Pilates trace. We wouldn't do it though. What we need to do is move on to this next table, and this is Maudsley's test of sphericity. This is one of your key assumptions. You want to make sure that your data meets the assumption of sphericity, because this means if it doesn't, you'd have to look at slightly different statistics in the subsequent table. So like most ANOVA assumption checks, you want this test to be non-significant. So if this test is non-significant, that means you've met the assumption of sphericity. You can see in this example here, it's non-significant, nowhere near being statistically significant, so we can say our data has sphericity. This means that when we analyse subsequent tables, we use the sphericity assumed line of data. If found this to be statistically significant, then there are ways of dealing with this with just the output that you already have, which will be described later in the video. So we've got sphericity in our data sets. This means in the subsequent table we can look at this line of data here, the sphericity assumed line of data. So what does this tell us? Well, it's a standard ANOVA output really. So what we can see is we have a statistically significant effect of drink type on the amount of words produced. You can see through the partial letter squared, it's quite a substantial, it's quite a large effect size. So we just report this accordingly, giving our F value, our degrees of freedom, our P value, and reporting the partial letter squared. Of course, this table just tells us that drink type has some sort of effect on number of words produced. It doesn't tell us which conditions significantly differ from each other. It tells us there is some sort of effect, and this is a statistical justification for exploring this further. The next table is the test of within subject contrasts. We don't really need to worry about this table, nor do we need to look at the test of between subjects effects at all. So really the only thing we're interested in is this one thing, the one effect: does drink type have a statistically significant effect on the number of words produced? Because it does, this means we can look at our estimated marginal means and, more importantly, our pairwise comparison table. The next table we can look at is our estimated marginal means table. These means here are identical to the means in the previous table. If you were to have, again, a more complex design, these means would actually be slightly different from the ones reported in the descriptive statistics table. It's because estimated marginal means are the means corrected for the presence of an additional variable. We'll come on to that in more detail in subsequent videos. All you need to know now is essentially these means are identical to those in the previous table. More importantly, what we want to see is which conditions significantly differ from each other. So we need to look at this table. Like in previous examples and the simple designs, the table gives you twice as much information as you need. When it labels the variables here, it just labels them as variable 1, variable 2, 1 and 3. These just simply relate to the very top what you've called them here, so we know 1 is alcohol, 2 is placebo, 3 is control. If we look at this table, what's it telling us? Condition 1, alcohol, compared to condition 2, placebo, are significantly different. And by looking at this, you can see that's because they produce less words in condition 1 compared to condition 2. Condition 1, alcohol, compared to condition 3, control, again, statistically significant difference, and again, that's because less words in alcohol condition compared to the control condition. The final comparison that we're interested in is condition 2, placebo, versus condition 3, control. As you can see, there's no statistically significant difference between these two conditions. The main effect of drink is driven by the fact that alcohol significantly differs from both the placebo and the controlled condition. The multivariate test table we can also ignore, and this is the profile plot. This isn't a particularly useful plot, but it does allow you to quickly visualize the data, and as you can see, we've got our 3 drink types: alcohol, placebo, control, and we can see how scores, the number of words produced, is much lower in the alcohol compared to placebo and the control conditions. Of course, you'd never report a graph that looks like that because it's lacking something fundamental, which is error bars. You should always have error bars when you're plotting means or estimated marginal means on a graph. Write these parts up accordingly, and this will allow the reader to fully understand that you had a main effect of the drink type on the number of words produced and actually what caused that when you drill down into the data with your pairwise comparisons. What is also notable as well, that if you were to have a Bonferroni correction instead of the least significant difference test, our results would still be statistically significant. This would probably still be 0.001, this would be 0.015, and that would be still obviously not statistically significant. So Bonferroni correction in this case would have had no effect on the conclusions that you drew from the data anyway. So this part of the video now is going to show you how to deal with violating the assumption of sphericity in a simple within subjects ANOVA. The data used here is exactly the same form of data as before, so no real changes, except I've gone through the figures, altered them a bit to ensure we violate this assumption. So we just run our analysis exactly the same way as we did before. We don't need to ask for anything different, anything new, all the necessary outputs are already there. And now you'll see in this example, we'll scroll through, and when we hit Maudsley's test of sphericity, you can see we now have a statistically significant effect. This of course means we've violated the assumption of sphericity, because these ANOVA check statistics, we want them to be non-significant. So this highlights that we've violated this assumption, and we must correct our analysis accordingly. So there's a bit of a two-stage process follows this. The next step, if we see this is significant, we need to look at the epsilon figure here. If this figure is greater than 0.75, we need to look at the Wynne-Felt statistic in the table. If it was less than 0.75, we'd want to look at the Greenhouse-Geiser statistics taken from this table instead. So we violate the assumption, we check our epsilon, and then we look at the appropriate statistics. So in this case, it's greater than 0.75, so we're interested in the Wynne-Felt line. As you can see, our degrees of freedoms have been corrected. So instead of being 2, as it is for sphericity assumed, we have 1.719, and instead of being 60, it's 51.57. So we report those statistics, and we'd write that up accordingly. Due to the violation of the assumption of sphericity and the epsilon group being greater than 0.75, a Wynne-Felt correction was applied to the analysis, and then we'd report these figures accordingly. As you can see in this example, it makes no difference statistical significance, the eta squared or anything like that. It's totally really in this example irrelevant, but in some cases when you do violate the assumption, you'll see these figures can change actually quite dramatically. In this example as well, just to finish it off, we can see we've got statistically significant effect. So we'd look at our pairwise comparisons, and this data set differs a little bit in as much as we now see there's a statistically significant difference in the alcohol and placebo condition, the alcohol and control condition, and in this case the placebo and control condition as well, which we'd write up accordingly. It is notable that some people actually recommend always using a correction when looking at within subjects ANOVA, and this, you may see this appear if you do any further reading on the subject, for several reasons really, but one key reason is this significance value which we use to judge sphericity is based upon probability. And what we know from probability is if we have a smaller sample, it is less likely to pick up a statistically significant effect. So if you have a small sample and do a within subjects ANOVA, you may violate the assumptions of sphericity but not have enough data to pick up the violation in this test. So some people will recommend always using the Winfeld correction. Don't necessarily need to do that, but it's worth bearing in mind that you could come across that. But I'd recommend using the epsilon as a criteria for choosing whether you use the greenhouse geyser or the Winfeld statistic if you find you've got a statistically significant Maudslay's test of sphericity.